Okay, in this video I'm going to talk about the angle between a chord and the tangent. So basically we have a circle here, we have a tangent and some point T, and we have a chord connecting the point T to some other point A on the circle, and we're interested in this angle between the chord and the tangent. So let's denote. So let's put some point P here just to conveniently denote angles. And so we are interested in the angle ATP, and like if we introduce the center of the circle, this would be the central angle subtending this arc, and the main theorem that I'm going to prove today is that the angle ATP is equal to half of the central angle, like half of this angle, half of the angle AOT. Okay, so let's prove it. So the first thing that we notice is that since O is a center, then OA and OT are radii of the circle, therefore they are equal to each other, and the radius OT is perpendicular to the tangent. So first we write that OA is equal to OT, because they are radii of the circle, and then the OT is perpendicular to the tangent TP, because the radius to the tangent point is always perpendicular to the tangent. So let's denote the angle ATP as alpha. Let's denote it as alpha. Now we can express what we will do is basically we will express the other angle AOT in terms of alpha, and we will see that this equality holds. So first we can express the angle OTA, right? In terms of alpha, it's simply 90 degrees minus alpha. So the angle ATO is equal to 90 degrees minus alpha. This is because OTP is 90 degrees, because of this. So now we have, because AO is equal to OT, so because of this, so the triangle AOT is isosceles, like two sides are equal, therefore the two corresponding angles must be equal. So the angle OAT must be equal to the angle ATO, and the ATO we already found, 90 degrees minus alpha, so this is equal to 90 degrees minus alpha. So both of these angles are equal to 90 degrees minus alpha. Okay, so now in the triangle AOT, in the isosceles triangle, we can express the third angle like using the sum of angles in a triangle. So the angle AOT is equal to 180 degrees minus the sum of two other angles. So minus 90 degrees minus alpha and minus 90 degrees minus alpha. Okay, and this is simply equal to alpha, because 180 degrees and minus 90 cancel each other, it remains 2 alpha. So 2 alpha. So AUT, so this is basically what we need, because AUT, the central angle, like this angle here, is equal to 2 alpha, and the original angle ATP we denoted as alpha. So the ATP then is equal to 1/2 of the AUT. So this equality holds, and this concludes the proof. So now there is a corollary to this theorem. So corollary that says that the angle between a chord and the tangent is equal to any inscribed angle, to an inscribed angle subtending the arc of the chord. Like, I'm not sure if we can say like subtending the chord, like maybe the term subtend doesn't apply to a chord, but because usually we say that it subtends an arc, not a chord. But that's basically what we need. Subtending the arc of the chord. So basically, let's draw a picture. So we have a circle, we have a tangent that touches at point T. We have a chord, and this angle is equal to any inscribed angle subtending the same arc of the chord. So this would be point C. So basically the angle ATP is equal to the angle ACT, and C can be any point on the circle. So like this angle would be the same, this angle would be the same, and so on. So like and why this corollary follows from the theorem that we proved is because it is a known fact that all inscribed angles subtending an arc are equal to half of the central angle subtending this arc. So yeah, and we just proved that the angle between the chord and the tangent is also equal to half of this central angle, therefore they're equal to each other. And the way to view this is basically like, since all these inscribed angles are equal, like so the way to view actually this angle between the chord and the tangent is an extreme case of an inscribed angle. So if we consider a sequence of inscribed angles that tend to point T from this side, right? So like we consider a sequence Cn that is closer and closer to T. So basically when let's say this C1, this would be C2, and so on. So when we consider a sequence Cn that tends to T, then the angle the inscribed angle basically would be, the inscribed angle is this ACT, right? So ACT, so the angle ACNT would actually tend to the angle ATP, because the chord CNT, the chord CT, when C tends to T, the chord CT would be smaller and smaller. It would be, and in the limit case, like would be equal to T. This would be the same point, and we can't make a line by only one point. But like we can prove that the sequence of lines containing this chord CT, so CNT, the line CNT would tend to the line TP. The line containing this chord CNT would tend to the tangent TP. So and then this angle would tend to this, and therefore it's no wonder that the limit case, so basically the ACT would be also equal to all inscribed angles. So the way to view this angle between a chord and the tangent is basically as a limit case of or an extreme case of the inscribed angle. So in a way it's also an inscribed angle, even though technically it's not, but it's an inscribed angle when C is equal to T, when C is the same point as T. Yeah, so basically that's it for this video.